Okay, so yeah, we spent the better part of almost 2 months learning the basics. We did do a little bit of quantum computing along the way. We looked at protocols like teleportation. We in fact looked at a very basic algorithm, the Deutsch algorithm. We looked at the no cloning theorem, etc. Right? But now we have all the tools that we need, or by and large, let's say most of the tools that we need to jump into quantum gates, circuits, and algorithms. So that's going to be the next big chunk. We'll probably spend a month or so doing this. So we already, so by the way, I want to mention that this is now chapter 4 of Nielsen-Schwarz, right? And I will very closely follow the material in chapter 4. So I encourage you to please read it. Much of what we've done so far is from chapters 1 and 2 of the book. Chapter 3 of the book focuses on classical computation, right? And I usually like to spend a few lectures talking about classical computational models, complexity classes, and so on. But given the shortage of time, in the interest of time, I thought I'd skip that. So what I will rather do is I will post some of my own lecture notes on that. And of course, I think chapter 3 of the book is a very good read, particularly for those of you who do not have a CS background. I encourage you to read chapter 3 because it gives you a very nice bird's eye view of classical, the theory of classical computation. Okay, fine. So quantum gates are not new objects to us. We've already seen examples of quantum gates. We are supposed to know mathematically what they are and so on. So let me first mention that what we're going to discuss over the next few weeks is what is often called the quantum circuit model. Okay. So the circuit-based model is one model of computation, right? It's not the only model of computation. This is one model of computation. And in this course, this is the only model that we will focus on. In some sense, that's what's been at the back of my mind for the last, month and a half of lecture. Now, what are the other models of computation? So one could today, talk about what is called adiabatic quantum computing. A special subclass of this goes by the name of quantum annealing. Okay, and a very closely related model is Hamiltonian computing. Now, these are unfortunately aspects that I will not cover in this course. So I encourage you to read up, online. There are several resources on this. If anyone is interested, you can reach out to me. I can send you some resources on this. In particular, I want to mention that the adiabatic model, which was a theoretical model proposed essentially by physicists rather than computer scientists, is today very popular because of this company that goes by the name D-Wave. Okay, their entire model of computation is based on this so-called adiabatic theorem. It is completely different from the circuit model, which is what we will discuss. The circuit model is what most companies today are building, whether it's IBM or Google or Honeywell, etc. This is the model that most companies are focusing on, but D-Wave from the beginning has focused on implementing what are called quantum annealers, and they claim to have been fairly successful at it as well, right? And like I said, once we get some theoretical hang of the circuit model, we'll have Chandra come and lecture us on the IBM processor. Okay, and the idea is for all of you to get some hands-on experience with the IBM processor, which of course is entirely based on the circuit model. Finally, I want to mention that from a theoretical standpoint, all these models are equivalent. Okay, and by which one means that it's possible to model any problem which you can frame in the circuit model can be transformed into the adiabatic computing model and vice versa, right? And what is more, they are all universal models of computation. Which means that it is not as if they can solve some restricted class of problems. The idea is that any problem can be translated into or transcribed into one of these models, whether it is an adiabatic or quantum circuit model. Hamiltonian computing is an attractive theoretical proposal, but it's not yet seen too much experimental action. I want to mention one more such theoretical proposal actually, and this is based on quantum random walk. Okay, so there is a quantum random walk based computational model, and this also is known to be universal. So universality means that any problem which has, say, a circuit model decomposition can then be mapped into any of these models. Okay, but all of these will be outside the scope of this course. What we'll discuss is we'll stick to just discussing the circuit model of computation, which is what we are all familiar with, even in the classical case. Okay, so this is also often called a gate-based model of computation. So this is also called Also, if you read around in any popular magazines and so on, you'll often find this word being bandied about, NISQ circuit, right? You'll often find this word being used. NISQ just means noisy, intermediate scale, quantum circuit. So you will often find this being stated in various popular newspaper articles, or if you read Physics Today or something like that, Quanta magazine or whatever. So this just means that today we have all these companies, Honeywell, IBM, Google, building gate-based or circuit-based quantum processors, which have noisy qubits and noisy gates, and these are small to medium scale, which means they have about 50 to 100 qubits. They have circuits comprising of 50 to 100 qubits and gates on them, right? Okay. So what are quantum gates? We already know what they are. So quantum gates, as we know, are essentially unitary matrices, right? So if I just check my attention to qubits, right, then qubits belong to, as you know, C2, right? So a qubit gate, a single qubit gate, must map pure states in C2 to pure states in C2. And pure states by definition are unit vectors of this form. And I think I showed you this earlier, that unitary operators, so since they are column vectors of this form, so single qubit gates are then essentially 2 cross 2 unitary matrices. Unitary because these are the norm preserving operations. And remember that we say that U is unitary, then U dagger is U dagger, U is identity. In this case, it's simply the 2 cross 2 identity. And this set of 2 cross 2 unitary matrices forms a group under multiplication. And this group, does anybody know what this group is called? The group of unitary matrices, 2 cross 2 unitary matrices.
Rotation matrices.
Rotations are a subclass of this, right?
SU2 matrices. Permutation matrices.
Okay, good. Permutations are also another example of this. Rotation matrices are examples of this. So SU2 is what I was looking for. Those of you who have done some physics courses should have encountered this group at some point, right? This is the so-called special unitary group. Okay. Now, so in general, the unitary group is just called U2. Okay, U of 2. If I want to talk about the unitary group or the set of unitary matrices acting on n qubits. Okay, so let me do this step by step. So now this is for a single qubit, right? And I'm going to call this group, it's a group under multiplication. So please check that if I take the product of two unitary matrices, right, and I call this W. So if both of these are unitary, yes, then W is also unitary, right? So of course, check this if you haven't checked this before. So this is what leads to the group property, right? Okay. Now, what is the special unitary group? So why do I put this SU2? U2 is simply the group of 2 cross 2 unitary matrices, right? What is SU2? There are MSc students here, right?
Ma'am, its determinant should be 1.
Yeah, indeed. So we call this a special, we call this, U is an element of the special unitary group if the determinant of U is 1, right? So without loss of generality, we can actually stick to just SU2 instead of U2. Okay. So what is normally the determinant of a matrix? Okay, so let's state some general facts about unitary matrices now before I jump to n qubits and all that. Some useful facts about unitary matrices. So what can we say about their eigenvalues? First of all, are they diagonalizable matrices?
Yes, ma'am.
Yes. So although they are not Hermitian, U is not the same as U dagger, but they are diagonalizable, right? Because U commutes with U dagger, right? The commutator of U with U dagger is 0. In fact, U dagger, U is identity. Okay. Now, what can you say about the eigenvalues of U? So if I were to write down U in a spectral form, right, like this, okay. Now, using the fact that U dagger U is U dagger is identity, what can you say about the lambda I?
Magnitude is 1.
Indeed, the magnitude of lambda I is 1. So, U dagger is therefore, remember, you can always do this lambda I star II, and then because of this property, so you use these two, and then you can show that modulus of lambda I is 1. So lambda I is complex, right, in general. This is not a Hermitian matrix. For Hermitian matrices, the lambda I's are all real. But for a unitary matrix, they are complex. But they're complex with unit modulus. What does this mean? Remember that every complex number can be written as the modulus times a phase, right? This is the argument, or rather, this is the, the amplitude, or the amplitude is 1. So there's only the argument in the phase, right? So this then is simply your phase, right? Now, what can you say about the determinant? So this is also true for all I. Yeah? So all eigenvalues of a unitary matrix are pure phase. Okay. Now, how can you express the determinant in terms of the eigenvalue?
Product of eigenvalues gives the determinant.
Sorry, can you say that again? I couldn't hear you properly.
Product of eigenvalues is determinant.
Okay, this is the product of eigenvalues. Right. But now, what can you say about the determinant of a unitary matrix? Because the eigenvalues are all pure phase.
It's also a pure phase.
Correct. So the modulus of the determinant is always 1. Right? What makes it special unitary is when it's not just the absolute value, but the determinant itself is 1. Do you understand? So the absolute value of the determinant of a unitary matrix is always 1. I hope you see that, because the eigenvalues are pure phase. But a special unitary matrix has its determinant itself equal to 1. And it's very easy to arrange for that by adding a scalar multiple, right? So that's why up to a scalar, we can essentially say that quantum gates belong to the special unitary group. The special unitary group has some very nice properties, right? And that is why it's useful to have them. Actually, the more general property of the special unitary group is that the determinant can be plus or minus 1, right? So let me just make this plus or minus 1, okay, for now. All right. Okay, so let's do some elementary examples. But before that, what about the n qubit case? So yeah, so please keep these facts in mind. In particular, the fact that the eigenvalues are pure phase. Okay, this will be very useful. In fact, this comes in handy in several quantum algorithms that we will do later. Okay. So what about gates on n qubits? So gates on single qubits are just 2 cross 2 matrices. Gates on n qubits are essentially 2 to the n cross 2 to the n unitary matrices. So again, without loss of generality, we will say that these unitaries belong to what is called SU2 to the n, the special unitary group of dimension 2 to the n. What is put in the bracket is nothing but the dimension of the space that these unitaries act on, right? Okay. So what we are going to work our way towards over today's lecture and the next lecture is to identify a universal set of quantum gates. Okay. But there are several steps that we must go through before we identify what universal quantum gates are. So first, let's look at a basic set of single qubit gates. So these are some of the gates that we already know. So I'm going to drop the sigma in the Pauli matrices, okay, from now on, because they'll just be gates for me, right? So instead of sigma x, I'll just say x. Sometimes I may use them interchangeably, but by and large, I'll stick to this convention that I'll call them x. X is the sigma x gate without the unit h bar by 2, because it's no longer, like I said, a physical observable at this point. I'm viewing it as a gate, right? And then there is y, which is 0 minus I 0. There is z, which is 1 0 0 minus 1. Then there is h, right? We've already seen the Hadamard gate. This is 1 over root 2, 1, 1, 1 minus 1, and it achieves the very important purpose of transforming the eigenstates of x to the eigenstates of z and vice versa. Okay, transforming from computational basis to the plus minus basis. Now, in addition to this, we will also need two new gates. So one of them is what is called a phase gate. Okay, so the phase gate is often denoted as S, and this is the gate 100I. Okay, what is the action of this gate? Now remember, this is how we depict these gates in circuits, right? So what is the action of this gate? Does nothing to 0, and it adds a phase of what? It adds an I to the ket 1.
Pi by
So what is the phase? Pi by 2. Yeah. So it actually adds a phase of pi by 2. And now if I have a superposition of this form, then this is transformed to this, right? So this is the action of this gate. So for example, what does it do to the plus state? What is the action of the S gate on the plus state?
It takes it to the like up state, means the plus state of the sigma y operator.
It takes it to the plus eigenstate of the sigma y operator. Good. This is what we call the plus I state, I think, which is nothing but 0 plus I 1 by root 2, right? That's the eigenstate of the sigma y operator, the plus eigenstate. And similarly, the minus state will be taken to minus I. So essentially 0 plus minus 1 over root 2 becomes 0 plus minus I 1 over I by root 2. And these are the eigenstates of y. These are the states which will lie at the intersection of the Bloch sphere and the y-axis, if you recall the Bloch sphere picture, right? So this is a useful gate. It's in some sense what completes this set, right? You had the z itself, which in some sense is what leaves the 0 and the 1 invariant. And then you had the h, which takes you from eigenstates of z to x. And then you have the s, which takes you from eigenstates of x to eigenstates of y. So this completes the that set. The last single qubit gate that we will need is what is called pi over 8 gate. Okay. This is denoted as T usually, although in some of the older papers you will find that this is sometimes called G pi over 8. Okay. I'm just putting this notation down because I don't know if you read other notes or other books, they may also use this notation G pi over 8. But I will stick to calling it the T gate. Okay. So this is another phase gate essentially, right? Except what is the phase that's being added now?
Pi by 4.
Well, yeah. So this adds a phase of pi by 4, but the reason it's called a pi over 8 gate is we'll look at that shortly. So essentially, okay, it adds a phase of pi by 4 to ket 1, right? But now you see, if I pull out an e to the I pi by 8, then this becomes this kind of a gate. Okay. Now, if you stare hard at this matrix that I've written, you will see that it looks somewhat similar to the Z gate, right? Looks somewhat similar to the 1, 0, 0, minus 1. The diagonal gate, right? Diagonal in the computation basis, right? And it is adding complementary phases to 0 and 1, right? So we'll see what, we'll find a way to represent this gate in terms of the Z gate. We'll look at that shortly. But this is the reason that it's called the pi over 8 gate in the literature. Okay, fine. So this is one basic set of single qubit gates. But then when I asked about unitary matrices, someone said rotation matrix, right? So let us write down, let us see if there's a way of looking at all these gates in a more unified way. Okay. The reason for wanting to have a unified picture is also from an implementation point of view. So every gate, remember, is some sequence of pulses that have to be applied on some physical system, whether it's a superconducting qubit, whether it's a nuclear spin qubit, NMR, or any of these architectures. So what sort of convinces that, I mean, I can keep writing matrices like this, right? But there has to be some structure, right? And unless there is some structure, I cannot even make a universality claim, right? And what is the universality statement? It says that there is some basic set of operations or basic set of gates from which all quantum operations can be realized. Is that noise coming from someone? Are others hearing this noise, or is it just me? Okay, I guess that is settling down. All right. So, yeah, so we have to start seeing some structure here. And the fact that we identified this as belonging to a particular group, whether it's U2 or SU2, that helps, right? So the first step in this is to actually be able to view these single qubit gates in terms of rotation matrices, right? And actually, these are called rotation gates in this language. So let me write down the rotation gate. So there are three rotation. Yeah.
Excuse me. What's the motivation of? Yeah, I mean, what exactly are we trying to do? What's the motivation?
What's the motivation for what? Sorry.
I mean, what exactly are we? You said we are looking at some structure, right?
Yeah. Yeah. So, like I said, the idea is to work towards a universality argument, right? Which means that there has to be a basic set of gates in terms of which all quantum gates should be realized. Okay, guys, I'm sorry. My audio is really, just give me a second. I'll fix my audio. Yeah. Okay. I hope we don't have any noise now. Is this better? Can you hear me now?
Yes.
Okay. So, yeah, so the idea is to be able to realize all quantum operations in terms of some basic set of gates, right? Sorry, this is not what I wanted. Let me just write down the universality statement and then maybe it will be better motivated. So a universal set is basically some set G of elementary gates in terms of which all quantum gate operations can be decomposed, right? So does there exist such a set, right? And remember, when I say all, I mean quantum operations on all dimensions, right? I should be able to take an n qubit quantum unitary gate and decompose it in terms of a basic set of elementary gates. Otherwise, no matter how theoretically amazing my model is, no experimenter is going to take this model seriously. Because if for every new algorithm and every new gate operation that you can think of, if the experimenter has to now find a new physical implementation, that's not going to work out, right? I need to have a basic set. So if I have to have a valid circuit model of computation, I must have a basic set of gates in terms of which, or a basic set of operations in terms of which all other operations can be broken down or decomposed. So in the case of classical computation, the statement is that all Boolean functions can be realized in terms of a few elementary Boolean functions. In fact, there are single Boolean functions like the NAND gate, which are universal, right? So no matter how complicated a Boolean function of n bits I give you, you can always decompose it in terms of NAND operations, right? Similarly, what is that elementary set of gate operations in terms of which you can visualize all other or decompose all other unitaries? And this heavily relies on some structure of this set of unitary matrices. That's what I was trying to say, right? Now, I wrote down a basic set of single qubit gates. I can write down more. No, I can keep writing down these kind of phase gates, more phase gates, right? I wrote down, so if you think about it, Z is a phase gate, 1, 0, 0, minus 1. Then I wrote down 1, 0, 0, I. Then again, I halved that, right? I wrote down 1, 0, 0, e to the I pi by 4, and so on and so forth. So I can keep writing gates down, but that's not the point. The point is to identify now some structure, some commonality between all these single qubit gates. Okay, and what we are going to show, in fact, is that all single qubit gates can be decomposed in terms of a basic set of rotation gates. Again, physics guys should be familiar with this kind of a statement. It should remind you of something from classical dynamics. What does this remind you of? Okay, let me describe the rotation gates and then we'll come to this. Fine. So there are these rotation gates are very much geometric sort of constructions. So the block sphere has these three axes, the x, y, and z. So the rotation gates are essentially rotations about the three axes of the block sphere. So it's basically taking a state, a point on the surface of the block sphere and rotating it about one of these three axes. We've already seen that x, y, and z gates are themselves specific rotations, right? Rotation by a particular angle. But now I want to write down a general rotation matrix, which is a rotation by any angle. So I'm going to call these gates Rx of theta, Ry of theta, Rz of theta, right? And this is how they'll be defined. So Rx of theta will be defined as e to the I theta x by 2. Okay. And your task now is to expand this and tell me what this translates to. I think you've already done, worked out exponentials of Pauli operators, right? So what does this expand out to? Similarly, this is going to be e to the, so it's essentially I theta by 2 y, okay? And Rz of theta is e to the I theta by 2 z. Does anybody remember what this kind of expansion works out to? Did you not work out something like this in your assignment 1? Okay, I should put a minus sign here. Sorry. Yeah. Okay, so let me tell you what this is, and it's up to you to work this out or check this out. So this is cos theta by 2i minus I sine theta by 2 x. Okay, this is cos theta by 2i minus I sine theta by 2 y. So there's a general statement out here that if I have a matrix A such that A is A is Hermitian and A squared is identity, right? So e to the I ax, right, is basically going to be cos x I plus I sine x A when A squared is identity. So this is the general statement for any matrix, right? So these are, you just have to first prove this for yourself and then you can work out, all of this follows from that. Okay, so please check this. Please work this out. I don't want to spend time here again working this out, but I think you worked out some version of this in assignment 1. Okay. Right. So now you can see that this is exactly one of the problems in the assignment. Okay. So now you see that the X gate and the Y gate and the Z gate are essentially specific examples of rotation gates, right? So what is the X gate? X gate is Rx of, what is the theta? What is the value of theta that gives you the X gate? Pi. Yes?
Yes, but with a phase. I think phase change.
Yes, indeed, there is a phase, but that phase does not matter, right? That's just an overall minus I, which doesn't matter, right? Okay. Similarly, if I have Y, right? This is also Ry of pi. So this is all up to some phase. So let me say that this is up to a phase of I, right? In all these cases. So okay. And you can also now visualize these as matrices, right? So you can also note that Rx of theta, what is the 2 by 2 matrix that it corresponds to? Remember, it's cos theta by 2i, so that's cos theta by 2 in the diagonals, right? And then you have minus I sine theta by 2 and minus I sine theta by 2, right? I'm just rewriting them as matrices now. Similarly, you can see that Ry is cos minus sine, sine, cos, and Rz is nothing but so note that in the definition, when I say that there's a rotation matrix with angle theta, the definition carries with it a theta by 2. Okay. Why is that? We can easily understand this from the Z example. Okay. And in fact, in the next assignment, you will prove a more general statement about this. But basically, this is what ensures that what you have is indeed a rotation matrix. This matrix should rotate by angle theta about the z-axis. This Rx should rotate by angle theta about the x-axis. And in order to do that, you have to define it with the half angle. Okay. So let's now look at the Rz of theta. So first note that now all the basic gates that we've written down can be visualized as rotation matrices or rotation gates with specific angles, right? So first we looked at this set, okay? The X, Y, Z are obviously these kind of rotation gates. What about the H? How will you view H as a rotation matrix? So H is actually, decomposing H in terms of a rotation matrix is a slightly non-trivial task. We'll come to that, but just note that H can be thought of as just X plus Z by root 2. Okay. So in some sense, if you have a rotation matrix that represents z and x, then you have a representation for h, right? Although the decomposition itself is slightly non-trivial, we'll come to that. And then think of the T gate. So what rotation matrix is T gate? It's easy to view T as a rotation matrix, right?
Pi by 4, RZ of pi by 4.
That's correct, right? And that's why this is called the pi over 8 gate, because this visualization is, the pi over 8 angle is what appears when you view it as a rotation matrix, right? Although it's RZ of pi by 4, right? But you see, up to an overall phase, it's nothing but RZ of pi by 4, which then has the angles plus and minus I pi by 8 in the diagonals. And what about S? Now S is nothing but T squared, okay? So essentially we have in some sense covered all the 6 basic gates that we wrote down there. In some sense we have covered them in terms of these rotation matrices or the rotation gates, okay? Now why rotation gate? So let's look in particular the RZ of theta, right? So we'll essentially show that RZ of theta rotates an arbitrary state by angle theta about the z-axis. So this is simple. I mean, we're just going to verify the statement. So RZ of theta acting on some arbitrary state psi, right? So this is nothing but cos theta by 2 I minus I sine theta by 2 z, right? This is acting on, remember that an arbitrary state. So now, since I've used theta here, I don't want to use theta phi for this arbitrary state. So I'm going to call this as, I'm going to represent the block vector notation for psi. I'm going to write it as cos alpha by 2 0 plus e to the I phi sine alpha by 2 1. Okay, instead of using the usual theta that we use. So then you can easily check this. So remember, it's just diagonal matrix with e to the I theta by 2 minus I theta by 2 and e to the plus I theta by 2. So if I pull out this overall e to the minus I theta by 2, then you'll see that this is nothing but cos alpha by 2 ket 0 plus e to the I phi plus theta sine alpha by 2 1, right? And this is indeed a rotation about the z-axis because it's not changing the alpha, right? So the others are slightly harder to show, right? Because there the alpha is also going to change when you rotate about the x or the y-axis. Remember this, right? And then you rotate about the z-axis. What is going to change is your projection on the xy plane, which is what is denoted by phi. So that is going to rotate by theta, right? So similarly, one can show, so I hope this is clear to you. So similarly, one can show, and I'll stop with this statement for today. One can show that Rx of theta and Ry of theta rotate an arbitrary state by theta about these respective axes, right? Okay. Now this you can check it will anyway show up in an assignment, right? Because it's important that you be able to visualize this on the block sphere and show that in fact, so this is the reason I said that the overall phase doesn't matter. So it's up to an overall phase, right? All these gates, we are defining some of these state, I mean, this also is up to an overall phase here, right? So this overall phase doesn't matter, right? Because this comes out here when you write down a state vector anyway, right? And what matters is only this relative phase here, and that's where the rotation by theta actually happens. Okay, so let me stop here. What we'll do tomorrow is to show that any single qubit unitary. So we have written down some basic gates and we have shown how we can write them in terms of these rotation gates. Although the Hadamard I've still not really shown you how to write it in terms of. What we'll see tomorrow is you can decompose any single qubit unitary as a product of rotation matrices with 3 different angles, right? There will be 3 different rotation angles in the block sphere, and any unitary matrix can then be written as a product of 3 rotation matrices, as a sequence of 3 rotations. And again, this is up to some overall phase, right? So this should remind the physics guys of something. Anyway,
Is this Euler angle concept?
Exactly, exactly. So this should remind you of Euler angles. And as you can see from a practical implementation point of view, this is very useful. And this is indeed what, say, the IBM architecture does. They have a way to realize these rotation gates, right? And if you manage to get high fidelity rotation gates for the block sphere, then you pretty much have any unitary operation that you can deconstruct, any single qubit unitary operation. So that's our first step towards making a universality statement. Okay. All right. So we stop here and I'll see you all tomorrow. Questions?
Ma'am, just a question. We said that all the qubit gates should be belonging to the group of special unitary matrices, but the S gate and T gate both have complex determinants. So
Correct. So
As
that's what I
discussed.
said, up to an overall phase, right? So I said without loss of generality, you can always multiply an overall phase and make it an element of SU2, right?
Okay.
So that's the point. Yeah. And I said the definition of SU2 should include the -1 also, which I missed. It's plus minus 1, right? And up to an overall phase. So that's why, yeah, technically it's U2, but for practical purposes, since this overall phase doesn't matter, we can bring it to SU2. Every unitary matrix, if you're willing to allow for this overall phase, account for this overall phase. Yes. Yeah. Yeah. Indeed. Yeah, I mean, that's why in physics, for all practical purposes, we only stick to SU2, right? Nobody talks about U2. SU2 has all these nice properties and it comes, you know, with this algebra of operators, the Lie algebra and all that. So, yeah, up to an overall phase, all unitaries belong to SU2. Okay, any further questions? Yeah. Okay, so I'll see you all tomorrow then, and we'll prove the Euler angle statement